All right, go sit down. Get off my platform. Put your late homework right there. All right. Who would like to sing and dance? Oh, sure did get quiet in a hurry. Barber? Mock knows you're in trouble now. See, he was mumbling while your lips were moving, and I thought it was you. All right. We have been doing influence lines. Lets you determine the maximum shears and moments inside of beams at various points on the structure. Lets you know where to put the loads in order to maximize those effects. One of the kind of trucks that we have running around loose make sure that's the figure 825, that's this figure here. This is an HS 2044 truck. They got it going in 1944 when they decided to standardize trucks so that we could design bridges so nobody would come in with something that was too heavy for it. It's 20 ton. 20 ton is right up on the front here, 40,000 pounds. And then there's another axle further back. And they call it an HS 20-44 truck loading. Now, if you've got some bridges out in the middle of nowhere that you can almost guarantee me that won't ever come by, then they have some HS 10s and some other things like that you can design for, some HS 15s, which are just proportionally down from that. Then they have a few standard standard truck loadings that just have just the front part. But whatever your bridge has to be designed for, here's a guy you can design it to resist. Shown from the top, the 8,000 pound load spread over two front wheels. The 32,000 pounds is spread over 16 and 16. It's standard 14 feet from the front wheels to the second set of wheels, and then this varies. That varies anywhere between 14 and 30 feet, and it's up to you to put it wherever it causes the worst grief to your structure. So probably a short truck would do more damage than just about anything, but it depends. Now that's a truck loading. Here is an alternate loading that they also make you design this structure for. A single concentrated load. If you're designing your beam for moment, 18 kips. If you're designing it for shear, 26 kips. All you have to have is one of them. And then a variable length of what they call lane loading, 0.64, 640 pounds per foot. And that's in each lane, just like this guy will be one in each lane. Generally speaking, when your spans are less than about 145 feet, this guy wins. More than 145 feet, usually this guy wins. If you've got a relatively short span, 50, 60 feet, there's not much doubt who's going to win. And if it's 200 or 300 feet, not much doubt who's going to win. For trains, if you start working for those people, that's a lot of train. It's a Cooper loading, an E72. The 72 refers to the drive axle loads. There's 4 of them in the front, one about half that size, 8 feet, 5 feet, 5 feet, 5 feet, about 9 feet to the second set. And they're 46.8 kips. Now, nobody's saying there really is one of these on Earth, and there's nobody really saying, good morning, there's one of these on Earth. It's a compendium of a whole bunch of things. It's about the worst, and if anybody's got something worse than that, you're going to have to tell us about it and let us go find out whether or not we think the bridges along the way will take care of it. They probably will be damaged, but if you grease enough palms, well, they'll give you a permit and they'll let you go across it. And then the taxpayers will buy us a new bridge in about 2 or 3 years. Happens. 2 of them, because you almost always have at least 2 of these things, and then everything behind it is 7.2 kips per foot as a uniform load. Don't you dare, I just started. I know you're trying, aren't you? It's so hard. All right, well, just practicing. Okay, pitch that back up here. That's a good one. Thank you. All right. Now then. Let's see, I must have missed a page here. No, that's okay. That's what he wants to do next. One of the ways to find out where to put a series of loads like that, if it's a single load, I don't have a problem. If it's a couple of wheels, I probably don't have a problem. But if you got a whole series of wheels like this, and especially if they have different magnitudes to them, then I'm not real sure whether you ought to put this guy right under the maximum ordinate or this guy and let this go down and let all these come back up or not. It's easy enough to tell, and you can do it just by brute force, and there's nothing wrong with that. For instance, I'd put the first wheel under the maximum ordinate on the influence line. Is that an influence line for shear or moment? Moment. Whoever answered in a hurry like that, that's good. You're figuring it out. If it was a shear influence line, it'd be looking probably something like this. Have a kink in it. You can do the same thing for a shear influence line. You'd put the first wheel, if you're looking for positive shear, you'd probably put the first wheel right here, and you put the second wheel right there, and so on, so on, so on, so. And if this was a 10 and that was a 30, I don't know if you'd win or not. But the way to find out would be to move the 10 on over to here, go ahead and put the 30 on the big number, and see if the added influence you get out of the 30 is bigger than you lost by having to put the 10 over there. And that's called the increase-decrease method. You just keep moving the wheels and see if things increase. And when they quit increasing and they start decreasing, then you've probably gone past the point that you're interested in. So the way to get it would be to say F1 times Y plus F2 times how high he is. Well, his height, as you see, is dropping at a rate, pick a slope here, whatever you want. Take this height divided by this base, and you have this slope. The slope would be M2. In this case, M2 would equal to whatever Y is divided by whatever B is. And that would tell you how the slope is decreasing, how quickly it's decreasing. So you'd multiply F2 times Y, except you're not supposed to take the whole Y. You're only supposed to take a proportion of it, minus the slope times X1 would give you the true height there. You multiply the true height times that wheel load. Then you go get F3. And the height that you would use, if you call this height Y, you could call this guy here Y2, call him Y1. He goes with wheel 2. He goes with wheel 3. You would say that Y3 is equal to Y1. And then you'd say, oh, wait, that's not right, because y1 is down, y3 is down this slope, and so you would subtract how far down you went down the slope times the slope. How far you went down the slope would be x1 plus x2 down that slope, m2. He's got an m1 slope on this side and an m2 slope on that side. And then you'd do all the wheels. You'd add it up. That'd be the max. That'd be the moment you'd get if this is the critical location of all those wheels. And if this wheel is 100 and this wheel is 10 and this wheel is 2, my guess is you've got the answer. In a truck, that's not likely. In a truck, we're going to have 8,000 on the front and 32,000 next, and then 32,000. So it's a pretty good chance that that might not be where you want to put the wheels. So then you move them. Now then you'll notice that F1 has decreased in magnitude. You can still find out what he is. Trying to remember if I started that thing or not. Because all you got to do is multiply F1 times Y1 and then realize, wait a minute, it's not supposed to be Y1. It's supposed to drop off at a slope M1, where M1 is Y over A, and then get the new number. And then multiply F2 times Y1 and so on. So you can always just beat it to death. You can always just go get the numbers, the wheels, stick them on there, and find the answer for where you ought to put all those wheels to cause the maximum moment at, or the maximum shear at a point in the beam. Now, if you'll notice that what you're really doing here is when you move this set of wheels from here forward on amount x1, you're really dragging everybody here up that same slope. So the truth is, wherever they used to be, they're going to be bigger by however far you moved them. In this case, the first move would be x1 times that slope. So that'd be another way to do it. The only thing that'll tell you, though, is the difference. It'll tell you the increase or the decrease. So here's an example. He's got a influence line which reaches, I'm not sure I like that, to 15 feet. I mean, just to be a purist about it, this is really generated by a unit load which caused an influence line of 15 feet in height, so that when you multiply 10 kips times the height of the influence line, you get a kip feet for the moment. And with that kip feet running around loose, pretending that you put a 1 kip load on there to generate this thing, then you get a 10 kips times 15 kip feet, which gives you 150 kip feet, which isn't right. So here he'll multiply 10 kips times 15. Here he'll multiply 20 kips times. He'll multiply 20 kips times 15. And then realize, well, wait a minute now, that is not that high. It is lower than that. This slope right here is 15 divided by whatever this length is, 20, 40, 60. It's 15 over 60. Each of these is 20. So 15 over 60 is 1/4, so the slope is 1/4, and it's a negative slope. It's going down. So multiply that times the height of 15 feet minus the slope times how far back the wheel is, 10 feet. And that's just for that one wheel. Then he'll have another 20 kips, but it'll be back down the slope 15 feet. And I have another 30 kips, and it'll be back down the slope 25 feet, and so on. Then when he moves them, this guy will have moved down this slope, while all of these people will have moved up the slope. And he multiplies them out, and he calculates how much moment you get for the different positions on the wheels. Then he says, don't forget, you ought to turn that truck around backwards, because although you say it's a one-way bridge, when the hurricane comes in and they turn all these things backwards, you better make sure it's still good. So here he has put the 30 kip in the front, and the 30 kip in the front, and then the 20-20-10, 20-20-10 going the other way. All right. The figure that goes with this is on page 292. What I'm going to look for is I know that you have done a masterful job of drawing an influence line for the moment at point A. And then you may have drawn an influence line for the moment at A minus 1. And then you may have drawn an influence line for the moment at A plus 6. And so you have thousands of influence lines here. And for each one of them, you can tell me where we ought to put the loads. But what I'm really looking for someday is the biggest moment that you can cause anywhere in the beam with this set of wheels. Right now, you can't tell me that. Right now, all you can tell me is that you guarantee me that if the boss is looking for the maximum moment that ever could be caused at point A, the answer is for this set of wheels. Then you drew an influence line and you put the wheels and you messed around with them until you found where the critical loading of the wheels were. And you reported M max at A, at X equals A. But that doesn't tell me that 2 feet to the right or 4 feet to the right or 8 feet to the right, there's not a bigger moment. That's what I'm looking for now. Here's the picture. I'm going to show you just 3 loads, although it's good for any number of loads. I've got a beam. It is of length L, and I'm going to arbitrarily choose the center of the beam as a reference axis. The maximum moment will not necessarily be caused at the middle of the beam. You say, well, it always was before. When I had a uniform load, it was at the middle. Yeah. When I had a single concentrated load, it was at the middle. Yeah. But once you have a whole series of loads like this, turns out it is not at the middle. You can put all the wheels at the middle all day long, and you can work around all much you want to, and you'll find that the moment you get, there's a bigger moment that occurs someplace else. So what I'm going to do is I'm going to put W1 at an arbitrary location. W2 is at A, away from that load. How long is that on a HS40, HS20 truck loading? How many? 22? 20? 15? 14? Do you want to take an average? Why don't we vote? Nah. How long is it? If you got that, you don't have a book. How would you remember that? I don't believe you. No, I don't believe you. I got to see it in writing. 14 feet. How do you do that? That's pretty good. See, you can do this stuff in your sleep. And then this one here, of course, varies. We're not going to stick a real number in here. We'll just call it A, so it'll be good for anything. And there'll be 3 sets of loads, or 3 wheel loads on this particular one. What I'm going to do is I'm going to arbitrarily move one of the wheels off a dimension X, and the distance between the Two sets of wheels in there is going to be B. And I'm going to tell you that the equivalent concentrated load on this beam is at a distance D. If you don't have a book, you got problems here, I can tell you already. Maybe you can just remember it. Okay? All right. Thank you. What I'm going to do on that free body, take a look at it in your book so I can work with it. I'm going to sum moments about the right-hand reaction. It's equal to, the reaction today is on the left-hand end. It is at a distance L. That's how long the beam is. Minus R is the equivalent concentrated force, wherever that turns out to be. Incidentally, you should be able to find where I could replace 15 wheels with a single equivalent concentrated load and give me an answer. What would that be? Yes, Muke? Oh, you don't have any idea at all? Well, ask her, text her. Hey, honey, I'm deep into it now. The guy asked me a question, and I didn't even hear the question. Doesn't matter. The truth is there was no question. Minus the single equivalent concentrated load that would replace where the truck, all of the wheels on the truck with a single load at its centroid, multiplied times, here's this guy, multiplied times L over 2 gets me here. I'm not here yet, I'll admit. Plus X minus D. To L over 2 plus X minus D. He uses parentheses D minus X because that's one of the terms he has drawn on the book, drawn on the figure there. Solve for the reaction today. Ha ha! Dismick, was that yours? Are you sure? Look at everybody pointing at the guilty party. I tell you, you guys are merciless. I tell you. That's better than some of the rings I've heard. Some of them are just horrible. Minus R times, we already did that. So the reaction at A, solve for R sub A. That would equal to, divided through by L, R over L times L over 2 minus D plus X. That's how big the reaction is. You're going to have to tell me R. R will simply be the sum of all your wheels. And you'll have to tell me where the centroid of it is with respect to one of those wheels, how far it is over. Now I'm going to compute the moment in the beam. Anytime you have a beam that's loaded like that, you always have a maximum moment under one of the concentrated loads. There isn't any doubt about that. At some time or another, the moment diagram will start at 0. It'll go up there. It'll either go up or down. It'll either go up or down. It'll go down to 0. It's going to be under one of those concentrated loads. So I'm going to try for underneath the load just to the left of this point. I'm going to sum moments about this point. I'm going to draw a free body of the left end of the beam. In other words, I'm going to multiply R sub A that we just got. I'll multiply it times its moment arm. Its moment arm will be L over 2 minus X. And then I will take into account W1 times his moment arm, A, and what's left over will be the moment inside of the beam. The moment is equal to R sub A times L over 2 minus X, what we said, minus the wheel that's still on the span to the left times A. A is the distance between the two loads. Plug that back into our equation for R sub A right here, and it solves out that the bending moment is equal to RL over 4 minus RD over 2. It's all of these terms here. And I'm going to tell you that that moment will change as you move the wheels to the left and the right slightly. Sometimes when you move the wheels a little to the left, this moment will get bigger. Sometimes when you move it to the left, the moment will get smaller. Therefore, if I take the change in that moment as you tinker with x and set that equal to 0, what you found is the slope of the moment as you change x. When you set it equal to 0, then that'll be when the moment is a maximum. So take the first derivative of this with respect to x. Term has no x, drops out. Has no x, drops out. Plus rd over L, rd over L, x, one derivative. Take the derivative, that's 2x to the 1, r over L, minus 2x to the 1 times r over L. Solve for x. Since it's 0, that says r cancels and L cancels. That says if you will locate the wheels such that x is equal to d over 2, you'll have positioned the wheel such that it causes the maximum moment. Looking back at what we're talking about, when x is equal to d over 2, you'll find this moment has reached a maximum. If you move the wheel a little to the left, things will start to drop off. If you move it a little to the right, things will drop off. And therefore, here's your job. This is what we're going to pay you for now. Number 1, tell me how big is R. The reason you need to know R, I don't know if you really have to get R. You could probably just go ahead and use the W's to solve for the reaction. Mr. Gitman, I'm doing great. You're a little slower than usual. Well, you're always here. That's good. I mean, look at this guy here is not here. That guy's not there. He's not here. She's not here. She's not. But Gitman's always here.
One day there'll be no one here. It'll be just me and you.
That's probably right. We'll get a lot of stuff covered. Next semester. Is that something you're hoping? Or?
Oh, yeah. I love this class.
No. I thought you meant that I wouldn't be here. All right. Oh, look at that. They finally got it. All right. So it'll be your job to tell me D. Where's the location for a set of wheels? Where is the centroid of that set of wheels located? And then it'll be your job to go find the center line of the beam, and then you will take the equivalent concentrated load position and the nearest biggest wheel. I got some bad news to tell you about the nearest biggest wheel. And you split them on each side of the center of the beam. You put the equivalent load on one side, and you put the wheel on the other side, and then you solve for the bending moment at that point by statics. You cannot find a location of the wheels that'll cause a bigger moment than that anywhere in the beam, no matter where you put them, no matter which wheel you look under. That's the biggest moment there is. So now, let me tell you the bad news about the nearest biggest wheel. If you're lucky, the nearest wheel will be the biggest wheel. But if you're not lucky, then you'll find that the nearest wheel is not the biggest wheel. And therefore, you'll have to do it twice. In other words, you'll have to move the wheel on one side of the centroid and move the equivalent concentrated load on the other side of the center line, and you'll split right down the middle, and you'll solve for the maximum or the moment under that wheel. So what you're looking for is you're looking for the nearest biggest wheel. If one of them is the nearest and one of them is the biggest, then you'll have to do it twice. So here's an example. How many of these did I copy? Did I copy that one? I copied a lot of them. Couldn't get them all done. That way we can scratch around on it. I've got a beam that is 30 feet long. Tell me when I need to pull this back out because you can't see it because I'll forget. The beam is 30 feet long. It consists of a 30 kip wheel, a 20 kip wheel, and a 10 kip wheel at 9 feet and 6 feet. Don't know if he solved for it. Let's solve for it. I don't think he did. He sums moment about this point right here to solve for what position the equivalent concentrated load would have. When I said you don't have to solve for R, I guess that was a waste of breath. It's not hard to solve for R, 30, 40, 50, 60 kips. It's location you do have to solve for. Summing moments about point G. Somebody got a calculator? Give me a hand here. Is equal to 0 is equal to 20. Oh, I'm already off. Thank you. Sorry. I heard somebody say something. I just wasn't thinking. Some of the moments about G is equal to 0 is equal to 20 kips times 9 feet plus 10 kips times 9, 10, 15 feet. And then I'm going to say minus an equivalent concentrated load. Let's put it this way, like it was a balance point or a reaction, minus the reaction, which is, or the equivalent load, which is 60 kips, times its moment arm, which is, I don't know, they call it X bar. And I can solve for the location. 5.5. Why does that not surprise either of us? So 5.5 feet away from the biggest load is the R. Truth is, it's not impossible that this guy here may cause the biggest moment. We'll have to see. So the first thing I do is I position the wheels such that the 30 kip load is the same distance away to the left of the center line as the resultant, so the single equivalent load is. Since that was 5.5, we're going to split it up half of 5.5 and half of 5.5. That means that this wheel is 2.75 out of 15, and therefore his location is 12.25. And his is, I don't care, because what I'm going to do is I'm going to think that with any luck at all, that's how I cut the beam, and there aren't any wheels to the left of it, and therefore all I got to do is multiply 24.5 times 12.25 to find the moment right here. M under this situation is 24.5 kips multiplied times 12.25. If you ever actually worked that out. Yes. Okay. Now then, since I may not be lucky today, rather than occurring under the biggest wheel, it might occur under the nearest wheel. And therefore I'll have to come and reposition all my wheels such that the 20 kip load is equidistant from the single equivalent concentrated load. That was 5.5 out of 9, so this one must have been 4.5, 3.5, thank you. 3.5, you're right, plus 5.5 is 9. So I come down here and I cut 3.5 in half. That's 1.75. And I move the 20 kip load 1.75 to the right. And I put the equivalent load 1.75 to the left. And then I cut off that end right there. Incidentally, now you got to solve for new reactions. It's because your reactions change because you move the loads. And if you would rather, of course, you can cut off this end. Either way, you got one wheel that you're going to have to also add into your equations. And your moment at that point will equal to, I'll leave it to you, I'm sure that's 26.5 kips for that reaction, times his moment arm. His moment arm is, I'm going to have to think about this, his moment arm is that long. Oh, there it is. It is 13.25. It is half of the length of the beam minus the 1.75. 13.25 feet. And if he wasn't there, that would be a full load multiplied times that full moment arm. Good morning, Gitman. Oh, that's not Gitman? You're kidding. Somebody came in after Gitman? How about that? So it's detracted 10 kips multiplied times 6 feet. Now, if I give you a hard time for coming late, please, go ahead and come late. You'll learn something. What? What do you mean, huh? I didn't learn anything. I can learn something. Maybe I'll start coming late, so I'll learn something. He says, if I come late, I'll learn something. And whichever of those two is a winner, bears a winner. That's the biggest moment that you'll find due to that loading condition. All right. Now then, that's the maximum moment. Somehow I missed something here, something good.
Are we going to do a review for the test on Thursday?
Yeah, tomorrow at 3 in the morning. What do you mean we're going to review? Read the syllabus if you don't know what's going on in here. Yeah. Well, I don't know what to say. You want a review?
Yeah.
Okay, who are you going to get to give it? Because it ain't going to be me. What are we going to review? What did we not review in here?
It's just those homeworks up to 5.18.
5.18? That's the only one you're having problems with?
Does that still stand? I mean, is that just it?
Yeah, that's it.
Yeah, I'm cool.
That's nothing.
Yeah, that's a review from last year, whatever.
Well, no, I think you've had time now to get your homework back is the problem. Now you got to get it in. That gives you a week, and then he's got to get it graded. And I think today you should have everything returned to
Got
you.
one more graded, but it's not even on the test.
Right. Well, as long as it's not on the quiz, I'm okay with that. That's all right. Yeah. No, I'm sure we still got some of your homework.
What about like the formulas? Are we supposed to have a formula sheet? Are they going to be on there? Is it supposed to be memorized?
There's no formula sheet.
There's no formula sheet. I'll give you anything you need. I mean, it's like this here. I don't know what you'd really.
Some of that wind load stuff.
Yeah, like
Yeah.
the stuff, and what about
I'll give you any graphs or anything else you need for any of that.
factors or like interior beams and all this? They're twos and these are fours.
No. Can't bring your book. No, that wouldn't work. Because I've done that before, where you try and learn everything, and during the quiz, that doesn't work very well.
So will there be stuff on like live load?
Oh yeah, oh yeah, oh yeah. What part of live loads have you not got?
Everyone's thinking of the reduction factors, whether or not we need to memorize.
No. All right, this is very little. I just want to know if you understand what we've been doing in here. Just like this stuff here. Have you memorized where to put the loads? You know, I hope you learned where to put the loads. So,
Workout problems, multiple choice.
yeah, multiple choice, A, B, C, D, E. So I take it you hadn't read the syllabus or looked at the syllabus? Not lately, have you at all? Be honest. Well, you have? Well, then have you seen about 80 old quizzes that I've given in years past?
I tried clicking on some.
Yeah, there were 305 quizzes on there.
Yeah.
Whenever I
It's
clicked
wrong
on
class.
Really?
it. Yeah. If you go up one level, it'll be thinking the 345 ones, but on the syllabus page, it is the wrong stuff.
Okay, you know, if somebody read the syllabus and tell me this, I'll sure be glad to put them up there. How did you get to them?
If it's like whenever you click before.
Hang on a second. There's somebody else would rather talk than you, and I can't hear you. Oh, hang on. I'm gonna. Just a second here. No, I don't need an eraser. I just need something to remind me. All right. Now, tell me how to get there
It's before you click into the syllabus page.
before you get to the syllabus
Yeah,
page.
before you click there, like on that same page. Once you clicked into the 345 class.
All right, let me just go there so they can go there too, because I didn't mean to hide these from you at all. I just had no idea they weren't showing. No. Well, I can't help you.
But if you go there, you're going to go to the wrong one.
All right, so whole class notes,
Sample exams and solutions. Those are
sample
right.
exams and solutions, mini sample, major sample exam. Okay. Nope, I really did. I know what happened without a doubt, because I made all these things the same time, and I must have gotten the 345 stuff and the 305s mixed. Old exams. Yeah, that's old 305. I can't imagine one of y'all really didn't call me and tell me. Let's just see if there's a chance here, because a lot of times something like that works. No. Well, I'll stick them up there as soon as I get out of class, because there's some up there. I don't know how many. Let's see if this looks like all of them. So that's typical of what I'm probably looking for. 6 pounds a square foot. Typical sulfur reactions. Draw deflected shape, draw moment diagrams, Major 2, we're getting off into stuff you and I won't be covering. All right, I'll post those. Where did that come from? That's Cahootix. Well, not really. That was a really good exam. Best I remember, I gave you guys that one. Yeah. Okay.
That was his test this year?
I don't know what year. No, it wouldn't have been this year, unless it was like during the spring. All right. Now, if you have a single load, then you could tell me where the maximum moment would be. For example, you would just simply take the load. This is the same load at different locations along the beam. And you draw me a shear and a moment diagram for the load here. Then you'd move it someplace else. You'd draw me a shear and a moment diagram. And it so happens if you put it at L/6, then you get 5/6 of P for the reaction. 5/6 of P for the reaction times L/6 gives you this number. Then you could move it someplace else and get the moment, and you can move it someplace else and get the moment, and you can draw what they call a moment envelope. But it's only good for a single concentrated load, but it does tell the boss the biggest numbers that he can possibly find anywhere inside of the beam due to the load going across the beam. And you just plot through all the points that you get, and it's just a curve. And so if he comes in and says, look, we're going to have splice plates here and here, well, you've got him covered. He can tell that the moment for the single concentrated load can't get any worse than those numbers. It's called a moment envelope. Excuse me. Thank you. Here's where he plots each of the values that you get. And again, if he says that he's going to put splice plates at the quarter point, he wants to know how much moment capacity the beam has to have at those points, then you can tell him. Maximum shear works pretty much the same way. If you have a shear influence line, then you can put the loads on the diagram. It's a little more complicated, obviously, because as soon as you move the big load that you had all the other loads trailing behind it, as soon as it moves across, it detracts. and then all the other ones will pick up. And again, probably just about as good a way as any is just to put the loads on there and work it out. For the case where you have a lane loading, namely a single concentrated load with a series of uniform loads behind it, you're going to always find that you get the maximum shear at the left end because it's the same as the reaction. If you are looking for the maximum shear that you can get in the middle, then that's what you'd do. You'd put the load, the concentrated load on it, and you would put a lane loading on one side of it, because that's what the influence line is going to look like. The influence line is going to look like that. So you'd put all your loads over on this side, and you get plenty close to the answer, just like here where you had a single concentrated load, wherever that guy went, and you run it across the beam. If you run this across the beam, it's really plenty close just to draw a straight line between those 2 points. Doesn't change enough to matter. So you get a shear envelope. So let's try one. I got a beam. It's 100 feet long. I've got a truck loading on it, 8,000 pounds. £32,000, 14 feet, and I got another 32,000 pound axle, and I'm looking for the maximum moment, and this distance varies between 14 and 30 feet. What do you think I ought to do with it? Long or short? Short. The more we bunch those loads up together, obviously the higher you'll get on the bending moment. I want to know the maximum moment that could ever occur in that beam. Now, let me go ahead and do the hard part. I'll solve for the center line. You tell me where the centroid is. Crank it out. I'll ask somebody at random, like Hunter. Or Getman. Do you know where the centroid of that set of wheels would be located?
Exactly? Or
No, yeah, right on the money to the nearest hundredth of a foot.
Are those 32,000 they saw?
Yes, sir. They're all 32,000s. They're a standard old truck. HS 20 means 20 tons, which means 40,000 pounds, which means the two lead axles. I don't know who came up with this numbering system, but they did. A total of 40,000 pounds on the front two axles. This is the steering axle. That's the drive axle. And that one goes where the other ones go. Some moments about this point right here to find out how far back the centroid is located. So it would be 8,000 times 0 plus 32,000 times 14 plus 32,000 times 28 ought to equal to the same tendency for a single equivalent concentrated load to roll about this point. Single equivalent concentrated load, 32 and 32 is 64, plus 8, 72,000 pounds. So if you replace all that with a 72,000 pound load at a distance x from the front wheel, you ought to be able to tell me where he is located. Thank you. 18 and 2/3, thank you, 0.67 feet. So this one, I love it. This one works out nicely because here's the, let me show it underneath it like it was a truck sitting on a single balance point. This dimension right there, excuse me, from the front. This dimension right here, for 18.67 feet. And that means I only have to do one thing because the nearest, biggest wheel is both the nearest and the biggest. So there's no doubt in my mind where to look. So we'll put a 32,000 pound load right here. Put an 8,000 pound load right here. And we'll put a 32,000 pound load right here. And we'll be kind of careful. 18, that's not a very good scale, is it? 18.67 cut in half would be 9.34. So this guy right here has to be 9.34. And your equivalent concentrated load has to be 9.34. Is that backwards? Okay. Could be. Well, no. Oh, from the thing. Thank you. Thank you. Yeah, it would be nice if you went from the wheel, wouldn't it? Thank you. He says, here's the guy we cut in half. Halfway between the reaction, or halfway between the equivalent force and the wheel, all right, is 14 from that. Thank you. 14.67, 18.67 minus 14, 4.67. So here's the 4.67. All right. Half of 4.67, 2.34, and 2.34. All right. Between these two wheels was 14 feet, and I don't think I care about the other wheels. I don't think I'm going to use them for anything. And I'm going to look under the nearest, biggest wheel, and I'm going to solve for the bending moment at that point. Okay. First, I'm going to have to get the reactions, a reaction. I'm not going to get them both. Some moments about this point right here to solve for the reaction at A. Some of the moments about B is equal to 0 is equal to 70, 32, 64, 72,000 pounds times his moment arm. His moment arm, if you want to take these individual loads, I guess you can. I just going to take the one we got, the one right here, 72,000 pounds. 72,000 pounds times 50 minus 2.34. Okay, let me write it down, then you can crank that in your calculator. 50 minus 2.34, and everybody will know where we got it from. And that's the total clockwise moment. because you were welcome to replace these 3 wheels with a single equivalent concentrated load, minus the reaction at A times his moment arm. The beam was 100 feet long. Thank you. Nobody wants to be the first one to say it, I know. Everybody looks at you, huh? Huh? And then solve for the reaction at A. The reaction at A is equal to Strout, 34,315. 2160334.
Well, now you're not going by proper sig.
Proper what? Well, then you would have told me 34,300. What's aggravating is I sat around and finally had to call somebody, and you knew the number all the time and wouldn't tell me. But that's okay. Yeah. All right. So now then we know the reaction, so we can sum moments about the max moment point.
Is that pounds or kids?
34,000 would be pounds. Thank you. Some moments about the cut face where we cut it under the wheel is equal to the reaction at A multiplied times his moment arm. His moment arm is 50 minus 2.34. And that would be the end of it if he was the only guy in the free body. But helping to resist him is 8,000 times 14. And the reaction today was 34,315. Inside of there's plus a moment. And therefore the moment inside the beam is, and it won't get any bigger than that. Move it a foot to the left, move it a foot to the right, check under another wheel. Doesn't make any difference. That's it. There isn't anything any bigger than that. Is there anything any bigger than that? No, there isn't anything bigger than that. Wheeler, is there anything bigger than that? Nothing bigger than that. See, certain things you can't do. You can't just stop if they wake up. You can't say the same thing too many times. They wake up. And sometimes they're really not asleep. They just like to do a number on you. So they'll sit there like this. And you ask them a question and they give you the answer. Just like that. All right, questions? Okay, how about shear? Here's the beam. It's 100 feet long. Where do you think we ought to be looking for the maximum shear? In the middle?
Right next to the support.
Right next to the support. That's always where the maximum shears are going to occur. So if you're going to use one beam from end to end, when you get in 344, they're going to ask you to pick a beam that has a web that will not cripple, that will not buckle, that will not shear. They're not supposed to do a bunch of things. And since you only get one beam for the whole thing, you'll look right here. Your influence line for shear will be the same as your influence line for the reaction at A. Here's the true influence line for the shear, slightly to the right of A. You take the beam home, you give it a unit kink, you bring it back on the job site, you put this pin in, you realize that this is off by the number 1, and you roll it down, and when you roll it down, it looks like that. Here's your influence line. Or, here's the beam. The influence line for the shear at A is the same as the influence line for the reaction at A. Therefore, you take the reaction and you move it up 1, and you get exactly the same influence line. Then you put your wheels on there. What? Already getting comments? No. Oh, here we go. We got some dissent in the troops, Booth. No. Well, I know you said no. I saw your head saying no. Sir?
I said serve.
Serve. Oh, I'm sorry. I thought you were telling me that I was doing something wrong here, which I was proud of you. Well, I would think that would have been a wise move. Yes, indeed. The truck goes the other way. Got to pry this out of you with a stick. 32,000 pounds. That's correct. 32,000 pounds. And 8,000 pounds. And 14 feet and 14 feet. And so we have the shear max is equal to 32,000 pounds. Adams, what are the units of this influence line? There are no units. Excellent. Remind me next time I ask you something, you're off the hook. Get out of jail free. There are no units on a shear influence line. Lightfoot, what are the units on a moment influence line? You can always pass that question on to your associate if it's so simple it's beneath you. Well, no, because the unit load always has no units. That's because when we multiply the influence line times our wheel loads and our uniform loads and everything, we want to get the right units for the answer. What are they? Feet is correct. So that's what they ought to come out. They ought to come out feet for an influence line for moment. Okay? So we got 32,000 pounds times 1 plus 32,000 pounds times 1, except we dropped some. We dropped 14 feet worth of downward pointing slope. So we dropped, let's just go ahead and write those slopes down. That slope is 1 divided by 100. I think the book calls that m, minus m times x. M is the slope, x is how far back down the slope you traveled. So in our case, that's plus 32,000 onto 1, minus our slope is 1 over 100, and our x distance is 14 foot back. That's 1 tall, 100 feet long for the slope, times 14 feet. Still leaves the number we're multiplying the 32,000 pounds times dimensionless. And then minus 8,000 times 1 minus a slope of 100 times 28 feet back. And whatever you get out of that, there's your maximum shear. Let's say it was a lane loading. I don't think the lane loading is going to control, but let's try lane loading instead. Instead of having a HS20, what does a lane loading consist of?
So why is it plus the 32 pounds and then minus the 8,000 pounds?
What? Thank you. I don't know why I thought I put a minus in there. some deep-seated psychological problem, no doubt. Well, yeah, that M is 1 over 100. All I did was I just, was showing you where these things came from. It's a slope. Lane load, lane load, lane load, lane load. There we go, lane load. Here's the shear. Here's the shear influence line, repeated. 100 feet long. Lane loading is how many kips? How many kips of concentrated load? Calling somebody else who probably knows but won't tell me. Mock? He probably knows. That's because Mock really didn't know, huh? All right. Barber?
No, Toby said he did.
What's in the book? I mean, I don't know it either. I don't remember. I got to go look it up. What is it? Got a book? You got a book? Okay. Has it got a page 284? Okay. It could have a defective book. You might want your money back. Is it there? All right. Lane loading, concentrated load, how much?
18 kips, we're only 26 for shear.
Okay, well that tells me the answer then. We're going to put 26 kips of load on there. Thank you. 26 kips at that point. And then Alahar, uniform load.
Just one kip or just one?
One, no. One kip, no. Keep guessing. What did you guess? If he's got a book right there, what's he going to do? Slap you if you borrow it?
Maybe.
8,000
8,000 pounds.
pounds. That's a truck again. A little further down of the lane, what they call the lane loading.
0.64.
0.64. That's right. So here we'll put a uniform load of 0.64 all the way across the positive area. If there was anything in there that was negative, we wouldn't put it on there. 0.64 kips per foot. And therefore our shear max due to a lane loading would equal to 26 kips multiplied times the magnitude of the influence line where it's located times 1 plus 0.64 kips per foot multiplied times the area under the influence line. Oh, I remember what else. Impact load. Times the distance between those, times the area under the influence line. The area under the influence line is 1 tall. It is 100 feet wide. It is a triangle, so it's 1/2. So that's the cross-hatched area under there. Kip per foot times foot gives us kips. Looking good. There's your maximum shear due to lane loading. Impact. I knew there was a page I missed. Impact. Well, if you won't tell me, I'll just tell you. Impact. Maximum shear. Huh. 285? Thank you. How did I go past that 3 times? Oh, it's down underneath railroad bridges. Thank you. Impact, page 385, page 386. Turns out that you always get some impact when these things go across the bridge. If they're little short bridges, they're pretty stiff. And when you drop something on something that is reasonably stiff, it causes a lot of extra load. If you drop something on something that's very flexible, the flexibility in the structure can absorb that impact, and you don't get as much impact load. You are supposed to take your numbers and multiply them times 50 divided by L plus 125. But in no case more than, they don't make you go above 0.3. So let's just say, for example, you had a beam and it looks like this, and it is 20 feet to the point that I want the answer, 30 feet, 30 feet, 20 feet. And I want the moment at this point, so I'll put a unit kink in here. I'm getting ready to generate the influence line for the moment at the center. If this pin rolled down 30, because it went over 30, then when you take it back on the job site, it's not going to fit. You'll therefore roll this up 30. This point, because you rolled it up 30, will go up 15. So this will be 15 feet tall. When you roll this thing down, it rolled down 30 feet. So you rolled it up 30 feet, and this one went up half as much, and so it has the units of feet. This point here goes below the line. It's only 20 feet out, where this guy's 30 feet out, so this will be 20 is to y, as 30 is to 15, so that'll be 10. And this one will be 10. And if I'm looking for the maximum positive moment, I would put my concentrated lane loading here, and I would put my uniform lane loading over here. And incidentally, I would put my dead loading everywhere. You don't have any choice but to put the weight of the slab itself everywhere, because it's always there. But the live load would go here. And the live load only gets impact. The dead load doesn't get any, because it doesn't run around loose on the structure. So this guy right here and this guy right here, these would have an impact factor to them. The impact factor would be, unless it gets bigger than 0.3, would be 50 divided by the length of your influence line when you're making this calculation. You're making this calculation now when it is 60 feet long. So it would be 50 divided by 60 plus 125. Give me a number right quick, we'll go home. All right. I was hoping it'd come out bigger than 30%, so I could show you how to say no and drop down to 0.3, but it's only 0.27. So your loads would be 1.27 larger than you calculate. All right. If you got any questions, stick around. If I was going to be here for the next few hours, I'd be glad to have a review. Nobody asked for one. Don't wait so late.
The exams are in class time, correct?
The exams are what?
For this course? It's during class time on Thursday?
They're during class, yes.
Okay.
Oh, yeah.
Okay.
Yeah.
All right, thank you.
Okay.